Favorite device. Yes.
I didn't hear what you said, but don't run with scissors, please. You ready, Landon?
Yeah.
No, I'm not. Hey, Avery Sanders, test for symmetry, work, graph, Lizzie, test, table of pain, graph. Guess what you forgot to do, Lizzie?
And
Draw
then
the other
for
half?
me, I
Yes.
just put the
Oh.
circle.
Cammy, I don't see her test, but she's got the table of pain and she's got the graph. And then we come to Landon and we see,
See it.
that's why you got a 1.
Gotta see it.
Wait, what is it? Oh my gosh.
We had this conversation before. Hey, you show me no work and it's just, especially something like that. That's not even like, you didn't even try to even copy down the answers.
No, I didn't even try to. I was just like doing what I thought I would.
All right, so any questions on the homework? All right, make sure your names are on and pass them left. We got 2 lessons left, today and tomorrow, and then we'll do a chapter review on Friday, chapter test on Monday. There's nothing challenging about today, just kind of all builds upon itself. Homework tonight. Hey, make sure questions, I don't know if it's literally 13 through 24, or maybe it's somewhere right around that. It asks you to also put it in exponential form. That's tomorrow's class. Today's class is not exponential form. It'll make more sense tomorrow. It doesn't make sense right now, but.
Hey, Mr. Charrier.
Yeah.
Do you like tea?
What?
Do you like tea?
Tea? I mean, I can honestly say that like sweet tea, yeah, and it's cold, yes, but not hot tea. My wife is like a hot tea person, like she always, anywhere we go, she gets tea. I'll occasionally have coffee, but the tea is, unless we're down somewhere down south and it's sweet tea, then nope. I mean, if I was cold, would I refuse it? No.
So.
You know where khaki came from?
You know, but did you drink?
Take a guess.
Milker?
Oh.
What are we talking about?
Tea?
Yeah, supposedly, I don't know if this is entirely true, but the story that I was always told was when the British Army went to India, they had white uniforms and all of a sudden they started getting
These things?
problems with being identified by the enemy in the sense of they wear white uniforms. And so they're like, we got to camouflage these things. So they took tea and used it to camouflage.
Did you drink tea in the military?
Maybe once, but like in an American MRE, you get coffee, you don't get tea.
Wow.
I worked with British soldiers a couple times in my career, and they're known for always drinking tea, and I don't remember them like.
Not drinking tea?
No, I just don't remember them like being a big deal about like, oh, let's. They always say like, let's put a brew on, and that just means make tea. But I don't. They were just as much coffee drinkers as we were. Thank you.
Surprised you like tea.
I didn't say I like it. I said,
Well, you.
I don't like.
well, where I grew up in the South, and like every restaurant you ever went to, that's you either got a soft drink or you got tea. That was, and usually it was tea.
And you like Diet Pepsi the most.
I wouldn't even say I like it. It's just like I need to have a cold drink. That's what, and something with cold drink and a little bit of caffeine. That's what.
Get like.
Drinking it like every day for the past like 5 years.
You're like Mr. Marco with
For-
Mountain Dew.
But-
But it's better because it's not Mountain Dew.
All right, ready? Now that we've gotten our tea conversation out of the way. All right, so weird words on the screen right now. This is tomorrow's class, and it's a weird day, but it's fine. We're doing this one today. So what we're about to do is really straightforward, really simple. You just haven't done it before, and it's difference, but there's nothing complicated. Today's nothing but a whole bunch of easy. Is what? It's an addition to that. Unfortunately. All right, crazy complicated class today. I'm gonna say it's mostly easy. There's a one little tiny bit that's medium, but it's mostly easy. It's all new, right? It's really hard to remember this stuff. Remember, we've done a lot of stuff, polar, rectangular, and there's conversion procedures for them. The same thing for today, just at a different form. And then tomorrow we get another different form. So I stated this at the start of the chapter, which is this chapter has a lot of resource card intensive stuff. None of it is necessarily all that complicated, although the thing that we just did for homework 2 nights ago, the thing where you had to do tests for symmetry, do a modified table of pain, that's the one procedurally wise that requires the most amount of work. But the rest is all pretty straightforward. All right, recall from way back when, caveman numbers are called natural numbers officially. Caveman, cavewoman could count, right? Probably did 20 or something like that. But those are the numbers that start with 1 and increase by 1. Those are called the natural numbers. Along came the Indians, not Native Americans, but the Indians, who said, hey, there's this number called 0. And when we add that to the natural numbers turn into the, hey, the numbers are not complete. They're called the natural numbers are now complete because we added 0 to them. They're now called whole numbers, right? The whole numbers are the natural numbers with 0 added to it. But wait a minute, business said, hey, if somebody owes you $3, that's 0 minus 3. So now we got to add.
Negative.
If you add negative numbers to the whole numbers, we get what are called the integers. But wait a minute, somebody said 4 divided by 3 is not up there. So now we got to add fractions and decimals, which are called the phone ringing. Mr. Chartier. She's on your way. Coley, go see Miss Rogers. Add fractions and decimals, and now we have the group of numbers called rational numbers. Thank you, right? Now, remember, the way this works is that every set of numbers above the word rational numbers are also part of rational numbers. I mean, 1 is a natural number, but it's also a whole number. It's also an integer. It's also a rational number. Any number divided by itself, that's a fraction, but simplified turns into 1. Well, what's left? Aren't there more numbers? So there's a group of numbers that isn't up here at all. Not yet. One more before that. She said it. What'd you say? Oh, no, I thought you said something else. Hey, these are the rational numbers. What are irrational numbers? Like pi, a decimal number that goes on, it can't be expressed as a fraction, right? So the irrational numbers, now notice, I'm not including 1, 2, 3. 1, 2, 3 are not irrational numbers. So rational numbers, now we get this set, doesn't include any of the other ones. They're a set all to themselves. Why is there a dot, dot, dot? Because I could do the square root of 2.1, and that's a rational as well, too. Right? Notice I'm not including the square root of 4, because that's a. Square root of 4 is it's any number up, it's all of these. Square root of 4 is 2, and 2 is a natural number, or a whole number, or integer, or a rational number. Okay, so all together, if we tie this in a nice bow, put them all in one bag, we call these the real numbers. But wait a minute. We have those set of numbers like here that are called, these are called imaginary numbers, I, right? Square root of -1 is defined as I. Square root of -9 is 3i, right? All of these together are now called, but imaginary numbers are not real numbers, right? They are not real. They're, well, by definition, they're imaginary, right? If we put a box around everything, we get to today's class, and today's class is on. What are these called? I put a box around all of this stuff. What are they called? Well, yeah, but there's a type of number. What are they called? Do you remember this from Algebra 2?
Whole number.
What? No, that's already there.
Real,
No,
Imaginary numbers,
no, that's just these right here. What are all of these numbers called?
not real.
They are called the complex numbers. So all of the numbers that you know are, you don't know any number that isn't complex. The only numbers that you know are complex. If this is true, then any number up here is a complex number, and that is a shock for some people, right? So any number that you can think of is complex numbers. Well, that includes both imaginary and real numbers. Like, wait a minute. Do you remember this from Algebra 2? All complex numbers, this took me a long time. I was in college before this kind of really sunk in. This sure looks like I'm doing what to two things. I'm not adding anything. I'm writing one number. But that number is complex. So even though this sure looks like I'm adding, yes, you are adding, but the reality of this is one thing, and this one thing is one number, and that number is complex, right? Complex numbers are written in the form of A plus BI, where A is the real part and BI is the imaginary part, right? We define I as the square root of -1. So the real part is the number in front of it. Now this could be a plus or minus because B could be negative as well too. But A is going to be the real part. Now the real part means it could be any one of those lists from the previous slide that says your real number. So it could be what was in that list. Could be irrational, it could be whole, it could be natural, it could be rational, it could be an integer, it could be any of those. The B is also a real number. That means that B part is how many i's do you have? If I have 2 i's, well, that's 2i. If I have square root of 3 i's, well, that's the square root of 3i. So even though this number, the blue part, the B part is attached to I is strictly imaginary. It's the square root of -1. It's never going to be I squared. It's never going to be I cubed. It's just simply going to be I. But how many of them do you have is the B part. And together, the B and the I make the imaginary part. Just remember, B is going to be a real number. Well, how many I's do you have? I got B of them. B could be positive or negative. It's always written as A plus BI. Sounds like you guys didn't write this down from last year or remember this. All numbers are complex numbers. All numbers. So complex numbers are the form of A plus BI. That's a complex number. But if all numbers are complex, that means you need to be able to write your number that you're thinking of in your head right now as a complex number. Well, if A is equal to 0, then guess what you're left with? So therefore, you're left with an imaginary number. So you've been used to writing imaginary numbers as I or 2i or 3i, but really, it's a complex number. You should be writing 0 plus BI. You can't add 0 to BI because that's imaginary. That's real. So this whole thing, 0 plus BI, is one number, and that number is imaginary. It's just BI. It's just that why would we write 0 plus BI when you can just write BI? So we don't write imaginary numbers as 0 plus BI, but we could. That same idea that we call BI a pure imaginary number, right? That same idea applies to real numbers. Well, what would happen if B was 0? Well, if B is 0, 0 times anything is 0. So therefore, you would be left with this. So therefore, you're left with A. So any number, any real number, can be written as complex number by adding 0i to it. But that sounds ridiculous. Why would you do that? Why you're making it more complicated when you just write A. So yes, in fact, 17 is actually A. How is that a complex number? Because it's really written as
17 plus 0.
it's really written as 17 plus 0i, but that's the complex number. Just the real part is the 17. And it turns out that 3i is actually an imaginary number, but written as a complex number, that would be 0 plus 3i. Can you wrap your head around that? This is one and only one number. It's just written this way in the complex form. All right. So, we good on that idea, even though you truly don't remember this from Algebra 2. Complex numbers. All right. Well, there was your review on algebra 2. Now comes the new stuff. So we all know how to graph in the rectangular coordinate system. Yes? Guess where I'm going with this? Well, we already know that as well too. We're going to be graphing complex numbers. Now, I said today is an easy day, so don't panic, right?
Wait, but like, what would you make the work when we made a polar coordinate system?
No. Because we're not graphing polar today, we're graphing complex numbers today. So we all know now how to graph polar as well too, but today's class is, what if I have a complex number? How do you graph it? Is that a complex number? How would you graph it? That's what today's on. How do you graph 5 plus 3i? Like, well, aren't I supposed to add something? No, this is a complex number. There's a real part and an imaginary part. You can't combine the real part with the imaginary part, but you can graph it. If you were to come up with your own rule and you wanted it as easy as possible, what would you do? I want to graph this. If you were coming up with your own rule of how to graph it, and you wanted to make your life easy, and no, Luke can't say, oh, just wouldn't do it, right? What would be the nicest way to graph that? What? Almost.
As a make one.
Say again,
make
Lucy?
one.
This is the imaginary, like the y is the imaginary, and that x is
Wouldn't that be pretty easy? Because then you would just need two numbers, and guess what they're always going to give you? And that is how it's done. All right. So graphing points on the complex plane is really easy, right? The only difference is which is the x and which is the y. Well, there are two numbers here, and wouldn't it be nice if one of them was x and one of them was y? And that's what we do. So there's nothing complicated here. This is in box 1. Write it down if you need it. Right? In box number 1, first off, all complex numbers are of the form of a plus bi. By definition, that gives us a as the real part, b as the imaginary part. And to graph this, here's what we're going to do. Why is this not clicking? There it goes. The real part is going to be your x. Landon, unless you want to wind up in the hallway, you better start doing something. And the imaginary part, notice it doesn't say I, it just says the blue part. The number in front of I. I is always just going to be I. You're not going to have an I squared. You're not going to have an I cubed. You're not going to have an I 51st, right? You're just going to have I. So the number attached to I, that includes if it's a 0 or if it's a 1, will be your Y value. And that's all there is to it.
Yeah.
Except you need to remember you're not graphing in the real rectangular system. You're graphing on the complex plane. So in the complex plane, the real axis is your X values and your Y values are your imaginary units. It's not complicated because it ain't complicated, but that's how you graph it. So when you look at A plus BI, you're looking at two things. You're looking at one and only one number, it's complex. And then two, you're looking at an ordered pair. I've got two numbers that can be graphed on the complex plane, where the real part is your X value and your imaginary part is your Y value. Just make sure when you graph this, you always tell your reader, hey, I'm not graphing XY, I'm graphing the real axis and the imaginary axis. They're not actually called X and Y, although we treat them as X and Y. They're called the real axis and the imaginary axis. Okay, so this is what a formal piece of complex graph paper looks like. They don't say XY, they say RE for real and IM for imaginary. I can't make this part complicated because it ain't complicated. Okay, so what am I going to graph? I'm going to graph 2, 3. And yes, I will insult your intelligence by reminding you that you be 2 units to the right and 3 units up from the origin.
Easy.
Easy.
Homework.
Well, we got to go through all the possibilities. All right, so where am I going to graph?
Left box.
Okay, so left 1, down 3. Okay, there's nothing complicated yet. When would it get complicated?
Right.
When it's not, it's looking like that.
When it's only a real. Or
When it's only a
imaginary.
real or it's only a pure imaginary number. So you just need to
Wouldn't
put
that just
your...
be on the axis?
Well, yes, exactly. But I'm just saying you got to think this through. So if you're provided with this, that is a pure imaginary number right here. So if we write this as a complex number, we would have to write 0 minus 4i, which means the x value is, and the y value is. Now I'm using x and y, but really remember real and imaginary axes. So the x value is blank, the y value is -4. So as someone already stated, this would live on one of the axes. In fact, it would live on the y-axis. Because that makes sense that it only lives on the imaginary axis, because the only thing here is pure imaginary number. What's the next one? Then what happens if you only have a real number? Well, to write this as a complex number, you need to add or subtract an I, a 0i, which would mean that the y value is 0. Now, I keep saying x and y. You're not going to see that in the math book. You're going to see the real part and the imaginary part. But let's use some common sense, and they certainly equate to each other in this particular case. Have I confused anybody? Oh, where's my dot? There it is. Easy. I said today's a bunch of easy stuff. So it's not. All right. Box number 2, new definition. I'm going to give you the following. I'm going to give you a point on the complex plane. Do you see it? Wait a minute. You wrote an equation. You didn't write a point. So here comes new idea number 2, I guess, for you. Points are not written with a capital letter and open parentheses. They're written as an equation. So z equals x plus yi means that this is the point z given this location right here. Okay? All right. Hey, I got a point right there. From previous classes, what can we do with this point? What did we do in the polar world always after we applied the point? We drew a triangle and what was the other part? What makes up 2 parts make up the polar world?
So always
The angle and the radius. So we could calculate, and we could calculate I'm going to choose the radius. How do you calculate the radius? Connect it to the origin and use Pythagorean theorem, which in this case we call, come on, you did this before, the distance formula, right? And what was so cool about the distance formula to the origin? It's just, in this case, yes, agree with a squared plus b squared. It's just agreed. So to do it, it's just, she said just a squared plus b squared. I said, and in this case, that would be x squared plus y squared square rooted. Remember? Well, that's easy, because if I give you the point, I automatically give you x and y, although you got to be careful, we're not really giving you x and y. We're giving you the real part and the imaginary part. So basically, all you got to do is take these 2 numbers and square them, and then take the, you can do that in your head, do it.
Wait, what is that?
So the I
It's
is
No. We didn't say do anything with the I. We just said take the 2 numbers.
then it's a 3, 4, 5.
Sure can. You told me I had to square x and square y. Well, that would give me. And then you told me to. No, you told me to do what first? Add, which will give me. What? 34. And then you would.
The square root.
So therefore the answer is root 34. Okay, you ready for change number 2? It's just a written change. Nothing changes in the original part. How do you find the distance? What changes is how we present it. I don't know. I didn't make this decision. I don't agree with this decision, but mathematicians decided we're going to give a new special word just for the complex plane, although it does apply to vectors. We'll see it again. For the distance between the point on the complex plane and the origin. And we are going to call that not the distance. Don't blame me. And we're going to give it a symbol as well too. And the word for it is, think of the vectors, think of vector words. Somebody said it. We're going to call that magnitude. And then we're going to call the distance. Do you remember? Maybe you saw it in physics. I don't know. It should be the same symbology they used in physics. Do you remember the symbol for magnitude? Do you remember the symbol for magnitude? Do you remember the symbol? Julia, you can't see what I'm doing. Do you remember the symbol for
Two
magnitude?
lines. I don't
It
know.
looks like absolute value, but it ain't don't blame me. I don't agree with that decision. It's confusing. It looks like absolute value symbols. But in the vector world, which we'll do for the next test, and then in this world, when we calculate the magnitude of a point on the complex plane, we use that symbol absolute value. But it's not called absolute value, it's called modulus or magnitude. It's just a fancy word for the distance formula, which is a fancy word for Pythagorean theorem. Calculating the length of the hypotenuse of the imaginary triangle that you draw from the point down to the x and the y-axis. Or just the x-axis, sorry. Almost universally, they always use Z, but it could be any letter. I said there's a whole bunch of easy, so we haven't got to the medium part yet. Tonight for homework, it's going to say calculate the magnitude. Do you even need to graph it to calculate the magnitude? Don't have to. If it says the graph, I believe it does say the graph tonight for homework. I think it says
Plot each
graph
complex
change
number,
to polar or not polar.
plot each complex number in the complex plane and write it in polar form.
Right, and write polar form, right. Does it say specifically calculate the magnitude?
Nope.
Guess what you have to do to put it in polar form. All right, to calculate the magnitude, you simply take these two numbers, square them. Remember, this could be, any of these could be zeros, right? Square them, add them, take the square root. Usually what happens is you forget to take the square root. You're like, oh, I just square both, add, you forget to take the square root. Everybody okay on this slide? All right. So how do you calculate the magnitude of Z? It's just the distance formula. And since it's going to the origin, all you do is square X, square Y, add them, take the square root. Do you need to write that down? Jaden's gonna be really lost.
It'll be fine.
He'll say.
Do you think he'll be fine?
Oh, no, I
People
think he's
say-
gonna come back screaming.
You will say sometimes, and then realize like if I stay here, ask for a voting.
No.
No,
Well, I mean, at least he's being honest.
no, we're gonna say that everything's changed. And he's still
I don't get any of
Everything's
this.
fine.
Everything's changed. Well, if he comes back, when the test is on Monday,
Just on Monday.
so it'll be fine, because then he'll start the second section, but it won't be like we're in the middle of something. All right, everybody good? All right. Well, we just did this one already. You told me the answer is for the magnitude root 34, square 5, square 3, add them together, and then take the square root. Okay? Two practice ones. Do we have to graph to do this? You can if you want, but really all we're doing is taking first one. What are we taking? Squared first, added, then square root. So Landon, the answer is first one. You?
Well, if you're gonna square it, it'll be Z squared equals 1.
Landon. No,
You're squaring both sides.
that's not what I said at all. You're squaring both values.
Values of Z equals -1.
It's not Z equals. We're squaring both values. What are the two values?
6 I and -1.
I is not part of the problem. Square both.
1 and then 36.
Add,
36 is 37.
square root,
Um. Would it be 6.2?
and the book isn't gonna ask you to round, they're just gonna say, what is the answer? So what's the answer? So guess what the answer therefore is? That's what the answer is. Okay? Unless the book, and it doesn't, unless the book says, give me an approximate value. Like if you're going to Home Depot and I need this as a piece of wood, then you know they're gonna look at you funny if you say I need the square root of 37 feet of wood, right? It would be 6.01, probably something like that. All right, second one, who can do it in your head?
25 square root 25.5.
Okay, everybody agreed it's 5? It's 5. Doesn't have to be a weird answer, it can be a nice number as well too. Are there any weird ones? So what would a weird one look like?
Because 0.
Well, they're not going to put the 0 in for you. What are they going to give you? They're either going to just give you a real number or just a pure imaginary number. Okay, so if they give you just a pure imaginary number, well, you still got to square both, but guess what one of them is?
Oh, a 1, right?
Not a 1,
0.
a 0. Okay, so square both,
0, 36.
add,
36.
and then take the square root.
6.
Okay. Do the same thing.
4.
Why you didn't do any work? Why are you claiming the answer is 4?
Square, you get 16, and then you square root that.
Okay.
4.
All right, smarty pants to the next one.
Well, you square root both zeros,
Okay.
so, or square them, so 0 squared plus 0 squared is 0, and then you square root it, and then you get root 0.
Okay, so Jackie and Luke were both trying to tell me what?
It's the same thing.
It's just the number that appears at the top if
If it's just a really just an imaginary.
if it's just a pure imaginary or it's just a real number, then it's just whatever number appears there, which could be 0. It also could be 1 as well too. Okay, does that make sense? All right, there's a couple like that for homework as well too. So it matches in red, matches. Okay. Well, geez, there's a whole bunch of easy stuff. When's it gonna be not easy? Well, it's always a but, right? Okay, so it's just the second game and it's not challenging, hard, it's just kind of medium. All right, we are going to convert from complex to polar, right? I'm not giving you all the conversions in one class because then it gets a little bit overwhelming. So we'll just got about 15 minutes left. We'll do complex to polar, okay? All right, it's a medium skill because it's got procedures, but make sure you show up to test day without a bunch of this stuff on your resource card. All right, so this is complex to polar, right? We know that this is what I'm going to give it to you when I hand you something in complex form, right? We just did a bunch of these, right? That's complex form. We also know that polar form has this conversion factor that if you see an X, you can write, and if you see a Y, you can write. Well, guess what? I see an X and I see a Y. So if this is complex form, and complex form has an X and a Y, and this is the conversion factor, I simply need to take this X and write. I simply need to take the Y and write. Okay. So what I just stated right there, what do you notice now? They both have an R, so I could factor out an R, and I'm left with this. And this in yellow, polar form. Okay? Well, that doesn't look that it actually is medium, but it certainly doesn't look medium at the start right now. It looks, okay, it's cool. It's just R parentheses cosine theta plus sine theta I, or I sine theta, however you want to write it. Book sometimes puts the I on the end. I don't like that because then you don't know if the I is inside or outside. I always put the I first. Okay. So, given complex, polar form looks like this. Okay, but here's the kicker. Polar form requires 2 bits of information. What 2 bits of information? They're in front of you right now. What 2 bits of information do I need for polar form?
Radius and
I need the radius and I need an angle, right? A degree, right? A radian. pick or choose whether you want, radian. I'm sure that tonight for homework, they put it in radians. Okay? R is easy to find. It turns out that the theta is the challenging part. Okay? So the I is just I. It's like there's nothing to calculate. I will always just be I. But you're gonna get the I from the I right there. Where are we gonna get the R from?
Or the magnitude.
Oh, R is the magnitude, right? So we're going to get the magnitude, in other words, R from the X and the Y squared added square root, right? So we're going to get that from the distance formula / Pythagorean theorem / magnitude, right? Because R is, and that's not the absolute value, it is the magnitude of Z, okay? Which leaves theta. How are we going to find theta? No.
Well, if you draw the triangle, isn't there like a?
If I draw a triangle, I can draw the triangle because I have the X and the Y, but we got some we could use for that. If we know X and Y, if you know X and Y, and we know R, in fact, we know all three sides of the
It's a
triangle.
90-degree triangle too.
So we could use some
Oh.
trig, right? Which trig you want to use if you're given X and Y? What? No. If you're given, now that's for non-right, well, it's for all triangles, but we got, as I point out, we got regular right triangle. So therefore we use easy trig. If I know Y and X, and I'm trying to find the angle, I could use. Somebody's saying it. Except we were trying to find the angle. So inverse tangent, right? So how are we we're gonna calculate theta from the fact that they're giving us X and Y, and we can use any one of the trig. But if they give us X and Y, we could use either sine, cosine, or inverse tangent. It's your choice. I'm going to show you the book uses cosine and sine, but if you want to use inverse tangent, you could. Oh, by the way, since the answer has it written in the form of cosine and sine, that's why the book chooses to write it like this. Okay? Well, what about this R? Well, it's okay because we're going to calculate R, and we calculate its magnitude. And they're going to give us X, and they're going to give us Y. Book chooses to use this one, but you could use inverse tangent as well, too. Okay? So we better write all this down, otherwise we're going to forget about it. So converting from complex to polar, you're going to take your complex. This is polar form, where R is the magnitude, and cosine theta is X over R. They're going to give us X. We're going to calculate R, where R is magnitude Z. And sine is Y over R. We'll have enough time to do about 2 examples. The thing that people will forget is that this doesn't say cosine of X over R. It says cosine of theta. So what I'm really trying to find is the angle. You're going to get the angle either if you're lucky, you're going to get it from your unit circle, or if you're unlucky, well, actually, if you're lucky, it won't be on the unit circle, which therefore requires you to use your calculator, right? That's the only way. If it's not on the unit circle, then we have to use a calculator. Hey, our calculator's been a whole different modes or methods, so I'm going to do it in radians today. So you don't have to change it from polar to function. You can leave it in polar mode because we're not messing with a graph. But you need to, for the answer sum units, you need to make sure you're in radians. I'm pretty sure tonight for homework it gives you 2 radians. Good. You ready to do the medium one? All right. We'll go through 2 or 3 examples. So here we go. Example. It says write this in polar form. How do I know that's complex? Yeah, but how do I know specifically that's in complex? If you see an I, it's complex. If you don't see an I, it's not complex. Could be real, could be pure imaginary, but it's not complex. Without the I, it's not complex. All right, cool. Step number 1, calculate the magnitude. So what's the magnitude? You can do this one in your head. What's the magnitude? I'm supposed to take the X, I'm supposed to take the Y, I'm supposed to square, add, square root. It's 2, right? The square root of 3 squared is 3, and this is a -1, but -1 squared is 1. So we got 3 plus 1, which is 4. And anyone who writes everything that I just wrote, I think you're silly, because you can do most of these in your head, right? No, I'm not calling you silly because you're doing it the right way. I'm just saying that this seems like a whole lot of work when most of you already figured out it was stupid. Just don't make a mistake. Okay, after you, are we okay? After you calculate the magnitude, now we're just focused on, by the way, that's what R is. R is 2. We got to figure out the angle. So how do you figure out theta? Well, we start off with this basic idea right here, that cosine theta, which is the first part, is x over r. Well, I know what x is. X is √3. I know what r is because I just calculated it.
It's 2.
So I get √3 over 2 for the cosine. Yes? What do you get for sine? -1 over 2, right? So this is my x and my y coordinate of the point. If it's on the unit circle, you'll recognize those numbers, right? Do you recognize these numbers as being on the unit circle or not? So if you recognize numbers, then grab your unit circle and tell me where you live. Tell me the angle of where you live. What is it? She got 11 pi over 6. Agree, disagree? This is the point right here, √3 over 2. I'm just looking at the unit circle. Hey, if this is √3 over 7, you ain't on the unit circle. Then you got to grab your calculator and do, which trick did we decide we're going to use? Inverse tangent, right? Y over x. Make sure you don't screw that one up. But luckily for us, we are on the unit circle. So on the unit circle, that angle is 11 pi over 6. I'm just literally looking at these two numbers, √3 over 2, comma, -1/2. It's on your unit circle. So now all I have to do is put all the pieces together. We've got magnitude, we've got theta, we got our form. Just plug them in. There's nothing to chug through. This is just plug in. So final answer is? That's the answer, right? It doesn't look pretty, but it's the answer. I mean, I'll call this medium. There's a bunch of steps here. The hardest thing is to find theta. And if you're lucky, it's on the unit circle. If you're unlucky, although I would say some of you might say, I'd rather it not to be on the unit circle, because then I'm just grabbing my calculator. Be careful what you wish for. That's what we'll do next. It's just a matter of being able to type it in your calculator, which if you have the magic fraction button, it makes it easy. If you don't have the magic fraction button, you get lots of parentheses. Yay or nay? Ready for the next one? Okay, here we go. 1 minus I. How do we know it's complex? It's got an I. It's complex, right? It's got a number. First step, change it from complex to polar. First step, calculate the magnitude. Can you do that in your head? Square root of 2, right? If you want to write out all the steps, well, x is 1, y is -1. Square both of those, that'd be 1 plus 1 is 2, so square root of 2. So r, or the magnitude of z, is 2. Square root of 2, sorry. I said the hard part is always calculating theta. Okay, to calculate theta, we start off with this knowledge right here, that cosine of theta, by definition, is x over r. Well, I know what x is. X is 1, and r is square root of 2, right? But can't have a square root on the bottom, so that will give me the square root of 2 over 2. Do you recognize that value as being on the unit circle? Okay,
Yeah.
if the other one is also on the unit circle, then we can look at our unit circle. If the other one is 1/7, it's not on the unit circle. Well, let's see what we get for sine. What do we get for sine? Y is -1 and r is 3. Multiply top and bottom by the square root of 2, and we get, you recognize that number as being on the unit circle. So this is your x, this is your y. Where do we live? I got √2 over 2, comma, -√2 over 2. Where does that live? 2 quadrant where? Quadrant 4, because X is positive and Y is negative, so it's not 2, it's 3. I'm giving it to you in degrees. 315 or 7 pi over 4. They're probably going to give it to you in radians. Ask now, forever hold your peace. So that's what theta is. Therefore, to write your final answer, you take your magnitude, you take theta. There's no chugging in, just plugging, right? Plug those values in, and you're done. Too quick or okay? Okay, maybe it's moving from medium to easy. Let's do one that where it isn't on the unit circle. And then call it a day. Because I got 1 minute left. No, 3 minutes left. Ready? Okay? Last one. There's always a but. What if you're not on the unit circle? You're going to know you're not on the unit circle as soon as you plug the values in. All right, magnitude, go. Root 7, right? 4 plus 3 is 7, square root of 7. Tell me if I'm going too fast. The people that get it, they get it usually pretty quickly. I probably wouldn't do any of that work. I would just, I mean, the numbers are nice enough that you can just do those in your head. Okay. What the problem is that we get now to theta for this one. So we start off with these two statements right here. This is just this is one of our identities for cosine to sine, x over r, y over r. Well, x is 2, but r is this ugly root 7. Okay, before you rationalize this, do a little bit of thinking. Save yourself some effort. Even if I rationalize this, is this on unit circle? So don't rationalize it. Just leave it that way. Yes, if you want open the book, they're going to show that you rationalize it next. You're just moving deck chairs on the Titanic at that point, right? We're going to have to plug this in to inverse tangent to find the answer. So I'm like, I'm not doing any extra work if I don't have to. Perfectly fine to leave this unrationalized to get an answer. Sine would be root 3 over 7. Once again, I'm supposed to multiply top and bottom by root 7. That just seems silly. I'm just changing the fraction for the sake of changing the fraction. It's not on the unit circle. So guess what you got to do now? But what's the order? Y over X. So guess what this actually is? Well, it's this, right, over this. Okay. So I need Y over X. There's my Y. There's my X. If we did a copy dot flip in this particular case, would that make it easier? In this case, yes. So if we did a copy dot flip, so root 7 over 2, we would get root 3 over 2, and that's what you should type in your calculator. Does that make sense? Or if you like a glutton for punishment, type that into your calculator. Your choice. So somebody do it. It's going to be a decimal number we're going to have to round. We're not on the unit circle.
I got 0.7.
2 decimals.
That'd be the same as if you just wrote it like as y over x from the original.
It would be, wouldn't it? It would be, wouldn't it? Yes. So what'd you get? Okay. I got 0.714. I did 3 decimal places. Everybody get 0.71.
Well, yeah.
Okay. Okay. You're looking like you didn't get it.
I just don't want to change the.
Okay. So you only had to do this because it's not on the unit circle. All right. Good enough? Questions? All right. The remainder of the year, like this is not going to change. Like every day, we're past the. I mean, you guys didn't know what a complex number was apparently at the start of class, so we're not going to come to any stuff that. Although, how much do you remember from vectors? Okay, so you remember calculating magnitudes or vectors? It would have been similar to this, right? So we'll do magnitudes of vectors, and we'll do dot product, cross product, things like that. I know you said you didn't know how to do that, but there's nothing. We'll do matrices after that. There's nothing familiar. We're going to do limits by the end of the day. You don't know what those are by the end of the year. You need to stay focused in order to pass this class, right? If you're not willing to invest any time, you ain't passing the class. All right, see you guys tomorrow. Julie, if you have any questions, send me an email.